Hi all, thanks for tuning in. Today's topic, we will be discussing metabolism. Let me get my PowerPoint pulled off. Okay, so you should have just finished. Sorry for the background noise. There's some construction going on outside. But you should have just finished our unit related to digestion and the physiology of digestion. And so now we're going to move forward and look at what happens next, essentially. So once those food molecules have been absorbed, so they've been moved from inside the digestive tract to into the bloodstream and potentially already processed within the liver, we're ready to use those in the processes known as the metabolic pathways. So we're going to take a look at those metabolic pathways now. So when we think about energy, again, what we're concerned with is the capacity for work, right? So energy is a dynamic state related to change. So we can't create or destroy energy. We can simply transfer it from one form to another. So when we think about bioenergetics, we're interested in the flow and exchange of energy within a living system. Okay, so bioenergetics, we're looking at how energy can be transformed and then utilized within a living creature. So energy metabolism is basically how our body can transform, use, and store these various types of energy. So a couple other terms to kind of make note of as we kind of start the fundamental basis of energy metabolism. We can have anabolism or catabolism. And anabolism, again, if you think about the term like anabolic steroid, anabolism is building up and catabolism is breaking down. Okay, so again, we need to be able to do both of those in order for us to appropriately configure food molecules depending on the needs of the body. Again, let's see. Energy is continually undergoing change is the other thing to note. So again, we're never going to be stagnant as it relates to metabolism. We're constantly either building things up or tearing things down, depending on what the needs of the body are, and depending on what you're providing the body as it relates to that nutritional piece. So we have 3 different types of work within the human body. And we can do chemical work, transport work, and mechanical work. And in these next slides, we'll take a look at what that entails. So chemical work is basically, we're going to take chemical energy from the food we eat and transform it into energy that we can use. Okay, so chemical work, cells perform chemical work for maintenance and growth. This could include storage of things. So again, storage of glycogen, which you can see here, storage of fats, which you can see here, and then also the building of proteins, which could be found in muscles or many other structures as well. Okay, so again, if we take a look here at the 3 types of nutrients that we might consume, we can consume proteins, we can consume sugars, we can consume fats, and we can convert these into a variety of things. Okay, so amino acids can be converted into proteins at the muscle. Also, if we overconsume amino acids, we could store them as fats. We can also convert some amino acids into sugars if we need to. Again, we don't want to do that process, and I'll talk about why a little bit later in this unit. But those are the kind of the fates associated with amino acids. Fats can really only do a couple things. One, we can use them for energy. And number 2, we can store them for energy at later usage. Okay, notice there's no arrows going from fats to amino acids or to glucose. So we can't convert fats into sugar and we can't convert fats into proteins. Okay, notice glucose is super versatile. Okay, so again, we can store glucose in the form of glycogen. We can also store some glucose inside of the muscles as well so that we can use it as a fuel there. If we overconsume sugars, we can convert those into fats as well and store those. Okay, so super versatile is glucose. Okay, transport work allows us to maintain electrochemical gradients. So this is important in the nervous system, important in cardiac systems for signaling, and also within the muscular system as well. So again, essentially what we're looking at when we think about transport work is active transport. And again, active transport is our ability to move molecules from an area of low concentration to high concentration. And because again, imagine that we're flowing upstream or upriver, imagine that we are going to need an energy input in order for those things to be possible. Okay, so within the nervous system, which you already covered, I was looking at my course calendar to see when we covered which. The nervous system, if you remember, we had to maintain an electrochemical gradient between the sodium and potassium molecules. And again, we did that in part through the help of active transport. And again, that requires us to have some energy input in the form of ATP. Okay. Mechanical work is simply muscle contraction. So again, this can look like a variety of things. We have 3 different types of muscle within the body. So again, you commonly think of skeletal muscle, and that's going to be the, the muscle that allows us to have movements occur. And that's super important. But we also have smooth muscle as well. And smooth muscle is going to help us to move food through the digestive tract. It's going to help us determine where blood might flow. So we have smooth muscle located in some blood vessels, and a variety of other locations as well. So again, think about movement as it relates to other items within the body. So blood, for example, but also, the digestive tract, looking at movement of foods. And then lastly, cardiac tissue, cardiac muscle is the heart muscle itself. So the contraction of that cardiac muscle is going to allow us to move that blood in general as well. So mechanical work could involve any of those 3 types of muscle that we have. Okay. So how does this work, right? So energy transfer involves transferring energy via those chemical bonds. So essentially what we need to do in order to get this ATP product, this magical product that we've kind of already alluded to, we can get those chemical bonds through the breakdown of glucose, fatty acids, or proteins, okay? Energy transfer is directly dependent on enzymes, okay? So imagine enzymes are going to help us speed up the conversion processes, okay? Let's see. I have a lot of notes here. So enzymes greatly affect the rate at which energy release can occur from these reactions. So again, an enzyme is going to help speed up the process, okay? So it makes things go faster. Enzymes are responsible for catabolism, or increasing the speed at which a molecule can be transformed from one form to another in the metabolism of foods. Not all enzymes operate under the same rate. So some enzymes are super fast and some are not as fast. So again, they can vary depending on what that enzyme is. Enzyme activity also varies depending on the temperature and pH within the body as well. So if we increase the temperature, that will help us to speed up the process. If we modify the pH, that can also affect the speed at which those enzymes work. Enzymes don't actually alter the reaction itself, so they don't actually change either the beginning or the end product. Imagine it as like I can drive my car to California and get there and establish that, path. I can do that. It's going to take a long time. Or I could take an airplane, right? An airplane would be significantly faster. And so imagine the enzyme is like the airplane, right? It allows us to get from point A to point B a lot faster than what I could do if I didn't have that airplane, okay? All right, so essentially we have 3 different energy systems. We have the ATP phosphocreatine system. We have the glycolytic system, also known as anaerobic glycolysis, sometimes called the lactic acid system. And then lastly, we have this oxidative system, sometimes known as the aerobic system or oxidative phosphorylation. Okay, so let's take a look at some of the components associated with each of these energy systems. Let's start with the ATP phosphocreatine system. And in order for us to understand what's going on with the ATP phosphocreatine system, we need to know what ATP is. Okay, so ATP is made of adenosine triphosphate. Okay, so here you can see adenosine molecule here, and triphosphate means that there's 3 phosphate bonds. Tri means 3, so there's 3 phosphate bonds here. Okay, so here you can see that adenosine molecule and 3 phosphate bonds. In order for us to get any energy out of this, we have to do a process called hydrolysis. Okay, when you think of the term hydro or hydrolysis, I would think that you would think of water. And in order for us to break down this ATP molecule, we have to do hydrolysis, which means the addition of water. Okay, so ATP is hydrolyzed via the addition of water. Okay, so basically what we're going to do is we're going to take an ATP molecule, we're going to add 1 water molecule, and via the addition of that water molecule, it's going to nip off. Let me get my little pen. It's basically going to nip off 1 of those phosphate bonds. So now I have a free-floating phosphate and a DP. And a DP, diphosphate, tells us that it now has 2 bonds. Okay, so we have 2 phosphate bonds and 1 free-floating phosphate. Okay, it's through the breaking of that bond that we get energy. Okay. So when we split that phosphate bond from the ATP, it releases somewhere between 7.3 to 10 calories, okay? So again, this is how we get all of our energy, is through this simple process of hydrolysis, okay? So how do we get the ATP in order to get this shit going, right? So let's take a look at the most basic of the energy systems, and kind of our first line of defense, and that is the ATP phosphocreatine system, okay? And in order for this to work, I need to have a couple enzymes. I need to have ATPase, and I need to have creatine kinase, okay? Again, both of these enzymes are going to speed up the reaction, all right? So I start with ATP. I'm going to add ATPase to the conversation, and that's going to split off a phosphate molecule, resulting in ADP and phosphate, and the release of free energy. Okay, so that's the first step. That's what we just talked about, the ATP hydrolysis on the previous slide. Okay, so water is also involved. I wish I had a touch screen. That would make things like a lot easier with trying to draw. Okay, so again, to kind of help things be like not so confusing, I guess. Just like we talked about on the previous slide, this is the ATP hydrolysis. Okay, so ATPase is the enzyme. Again, we're going to add water into the conversation. That's going to take one of those phosphate molecules, split it off. So now I have 1 inorganic phosphate and an ADP molecule, and the splitting of that bond allowed me to release energy. Okay. The next thing I'm going to do is take a molecule that I have stored within the muscle cell that's known as phosphocreatine, or creatine phosphate sometimes. And now what I'm going to do is I'm going to take this phosphocreatine molecule, I'm going to split that off through the help of creatine phosphokinase, and that will give me a creatine molecule and a phosphate molecule. Now what I'm going to do with that phosphate is I'm going to bring it up here, and combine it with ADP. So I'm going to take this phosphate, I'm going to combine it with ADP, and that's going to allow me to produce a new ATP molecule. Okay. So again, I can continue to do this for A as long as I need to, or B until I run out of phosphocreatine that is stored within the muscle. Okay, so how much energy can we get from this system? Somewhere between 3 to like 12-ish seconds is about right. Pros and cons of utilizing this energy system. Number one, it occurs in the cell cytosol or the cell cytoplasm. Number two, it's very fast. Okay, so this is the fastest of the systems to be activated, so it can give us energy very, very quickly. The system is super powerful, so if I want to do something that's short in duration but with a high amount of power, this system is my go-to. Okay, cons associated with using this system are essentially that it gets fatigued super easy, right? I can only do activity for up to 12 seconds with the use of this particular system. Okay, so I'm limited by the amount of phosphocreatine that I have stored within the muscle itself. Okay. Next system to take a look at is known as the glycolytic system, also known as anaerobic glycolysis, the lactic acid system. Those are just a couple examples of how you might see this listed in different textbooks and different sources. Okay, so glycolysis, oops, come on. Glycolysis, it simply just involves breaking down one single glucose molecule or one sugar molecule into pyruvic acid, or sometimes it's called pyruvate, right? This process is anaerobic in nature, which tells us that it does not need oxygen in order for this pathway to occur. Okay? It yields a produce of 2 to 3 ATP and also 2 NADH molecules. Okay, these NADH molecules we can cache in a little bit later down the road to get more ATP in the aerobic pathways. Okay, it involves 10 to 12 enzymatic reactions in order for this pathway to work. Okay, pros and cons of using this system. It doesn't really produce that large of an energy yield, but it does serve as a pathway into the next system, which is the aerobic system. Also occurs in the cell cytosol or cell cytoplasm. It's kind of like your intermediate of the system, so it's moderate in regards to energy production capacity. It's moderate in regards to fatigability. So again, it's just kind of like your middle of the road system. It can last you up to about 2 minutes in duration. Again, doesn't require oxygen in order to do so, and it's of moderate power. So again, it's not as powerful as ATP phosphocreatine system, but it is more powerful than the oxidative pathway, which we'll talk about next. Let's see, other things to note. It does produce a kind of taxing waste product that we'll talk about next. So again, those are kind of some of the pros and cons. So it's moderate for fatigability. Its intensity level, you could say you could hold this like 88%, 87% intensity for up to 2 minutes or so. Yeah, so let's take a look more detail. Okay, so again, I said that there's 10 to 12 different enzymatic activity reactions occurring in order for this pathway to complete its job. Okay, so again, you start with glucose, or that simple sugar molecule, and it's reconverted into a variety of things before eventually it produces, or it converts itself into pyruvic acid. Okay, and within this system, again, we can think about the speed of this system occurring as it relates to one rate limiting enzyme. Okay, so I want you to imagine that you are a factory owner. Okay, and let's say in your factory you're trying to make, let's go teddy bears. Okay, so you own a teddy bear factory. Okay, And so in order to make your teddy bears, you're going to start with the fur. Okay, so somebody's going to sew the fur together. And then somebody's going to put the stuffing in. And then somebody's going to sew the buttons on for the eyes. And then somebody's going to put it in the box. Okay, until at the very end of my factory, I have this teddy bear that's ready to go. It's in the box, everything's done. Okay. How fast can I make this teddy bear depends on the rate limiting enzyme, okay? Or the slowest person on this assembly line. So who takes the longest in order to get their task accomplished determines how fast I can make a single teddy bear or how many teddy bears I can make within X amount of time, right? So again, if this person's job was to, let me go back. This person's job was to sew the lining together, and this person's job was to put the stuffing in, and this person's job was to sew the buttons on for the eyes. And let's say this person is the slowest person, right? He's the rate limiting enzyme. He determines how fast we can produce teddy bears. This guy can be awesome at his job, but if this guy sucks at his job, he's the one that determines how many teddy bears we can produce, because we're not sending out teddy bears without eyes, right? So again, the rate limiting enzyme is super important for us to take a look at, because that determines the overall rate of this process, because it is fairly complex. So the rate limiting enzyme in glycolysis is known as PFK. That's good enough. You don't need to know what that really stands for, because it's a lot of letters and things like that. But again, I do want you to understand what it means to be a rate limiting enzyme, right? It's the slowest enzyme in the sequence of events, and so therefore it determines the overall speed at which the process can occur. Okay, so we've talked about what's going to happen with that glucose molecule, or again, here it's listed as a sugar molecule. So sugar, or this glucose molecule, is converted into pyruvate or pyruvic acid, which you can see here. Okay, so what happens next is determined by which pathway you'd like to follow. Okay, so again, if I am anaerobic in nature, I'm going to take this pyruvate, I'm going to convert it into lactate through the help of an enzyme known as LDH. Okay? If I want to go aerobic in nature, I'm going to take that pyruvate molecule, I'm going to convert it into acetyl-CoA, and it's going to enter into the aerobic pathways. Okay? So, again, what determines the fate of this pyruvate molecule? How do we know whether it's going to become lactate or acetyl-CoA, right? So again, it depends on how fast we need these reactions to occur. Now, I would like to do this. I want to do the aerobic pathway. This feels better. This is less painful, okay? So again, following this aerobic pathway is nice because it doesn't produce as much waste product. Your body would prefer to take this pathway. However, this pathway is slower. Okay, so imagine that I'm doing something with high intensity. Let's say I am running an 800 meters in track and field. Okay, and so I'm going at like 95% intensity in order to run my 2 laps on the track. Okay, so I'm going to start by choosing this aerobic pathway. But that's not enough. That's not enough for me to keep up with my opponents. That's not enough for me to put forth the most effort that I possibly can. Okay. So once I've maxed out this aerobic pathway, my next bet is to go this way and produce lactate. Okay. So the only reason that I'm ever going to produce lactate is because I've maxed out this aerobic system, and so therefore I have no choice but to use or to produce lactate because I need more energy in order to complete this task that I'm asking of myself because the intensity is so high. Okay, so that is when we choose lactate. Okay. So what happens once I do produce this lactate? What happens next, right? So lactate can do a few different things. Again, lactate gets a really bad reputation. Again, you've probably heard like, oh, lactic acid burns your, makes your legs burn and things like that. And that's partially true. However, lactate can be reconverted into some good stuff. So lactate can be carried in the blood and carried back to the liver and reconverted into sugars so that we can reuse it. Again, I've got to stop running that 800 meters in order for that process to occur. So again, keep in mind that I can only do this for 2 minutes and then I will recover, right? So again, we can convert that back into glucose. So it's not all that bad. Not all that bad of a guy. Okay. So essentially, what happens is the cell, if we're looking at why this process works or why we're doing this process, okay, this molecule, NADH, that H is kind of problematic for us. This is acidic. And within the cell itself, it doesn't want to be acidic. Again, remember that I'm running this 800-meter run, and in my legs, I'm getting a lot of, this buildup in my legs. Okay, this acidity associated with this H molecule is bad news, right? That's something that causes a burning sensation. So what I want to do is I want to get this out of the cell as fast as I can. Well, the way in which I can get that H or that acidity out of the cell so that I can continue to do work is converted into lactic acid in ADH, or NAD, sorry, NAD. NAD is no problem, okay? We got rid of that acidic molecule, and basically what we did was we hooked it into this, and that produced lactic acid, okay? Lactic acid is a very chemically unstable molecule, so the body doesn't like to be in that form. So almost as quickly as it forms lactic acid, it'll reconvert itself into lactate and one hydrogen molecule. Okay. Again, lactate, not so bad. This hydrogen molecule, this is what causes the pain in your legs, for example. So if you've ever, lifted and you were doing a set of 15, or you were doing a wall sit, or like I said, you were running a 400-meter dash or whatever, and you feel that burning in your legs, okay, that is from buildup of H. Okay, so this H is the bad guy. Lactate, not such a bad guy. Okay, so again, essentially, now I've got this lactate in the blood and also the H is in the blood. So it's not the problem of the cell anymore. And that's really what the cell wanted, was to get it out of that particular cell so that it can continue to do more work while we get rid of that lactate and that hydrogen molecule. So again, when we think about this system, we're looking at, 90 seconds of moderately high intensity. I already gave you the example of an 800-meter run in track and field, but can you think of some other sports where anaerobic glycolysis would be really important, right? So again, I'm going to go pretty hard for, up to, 1 to 2 minutes in duration. Okay, so some examples, wrestling, absolutely. So again, a wrestling match lasts 7 minutes, as long as somebody doesn't get pinned. But there's going to be some stopping and starting. So this system is their bread and butter, right? So again, I'm going to go as hard as I can for 1.5 minutes, and then we go out of bounds, and then we're going to come back to center, and so on and so forth. So very important in the sport of wrestling. Basketball would be another example. Okay, so again, I'm doing a couple fast breaks. I need to run as fast as I can, and I need to be able to jump as well as I can in order to get the rebound, etc. Soccer would be another example. Some of those intermittent sports, we're going to really rely on this system in order to allow us to produce a large amount of power. Okay. So one of the things that's important for us to note is how this really applies to what we do. And again, I know I'm a nerd and I know I'm getting a little bit ahead of myself, myself as this is just physiology and not exercise physiology, but I want you to kind of see how this applies to training, right? So here I have an example of lactate threshold. And lactate threshold is the point at which blood and muscle lactate levels are going to increase abruptly, okay? So it's an intensity associated with around 87%. I know I'm very precise, but I'm very interested in the lactate threshold. Okay, so basically we're looking at how much lactate is in the blood continues to rise. So we're comparing how much lactate I'm producing with how much I am able to clear or convert back to sugar. Okay, so below this 87%, I am producing some lactate. However, I'm able to take that lactate to the liver and get it converted back into glucose. And so everybody's happy. Okay, so I only have a blood lactate level of around 2 millimoles per liter. Okay, but as I mentioned, once intensity rises and I get above what's known as the lactate threshold, I'm not able to clear that lactate as fast as what I could at this lower intensity because I'm producing more. Okay, so essentially what we're looking at is the ratio of lactate production in comparison to lactate clearance. Okay, so how is training affect this? So I know there are some cross-country people in this class. So again, when we think about work like tempo work, right? So doing a tempo workout, what we're trying to do is we're trying to push our lactate thresholds to the right, okay? And so essentially what that allows us to do is work out at a pretty hard intensity, but it's not all out, right? So a tempo run, for example, should feel like about 87%. Really what we're trying to mimic here is doing work at that particular intensity, okay? And so by doing work at that intensity, it allows my body to become better at clearing that lactate. So with training, I'm then able to shift that lactate threshold to the right. So before training, I was able to run at a speed of 10 kilometers per hour before I really started to build up lactate, okay? After training, I've improved that so that now I can run at like 11.7 kilometers per hour before I start to have that buildup of lactate, right? So again, I can do more work, I can run faster prior to having the buildup of lactate. And the good news with this is if I stay on the left side of the lactate threshold, I can continue on for a long freaking time, right? If I get above that lactate threshold, I'm limited in how long I can continue to go before I have to stop because I have too much waste products built up. One other thing to note here would be what happens on this top end, okay? So again, notice that before I started training, so as an untrained person, I could tolerate about 9 millimoles of lactate in my blood. That was like the absolute maximum that I could allow myself to get to. But with training, look, I can improve my top end. Okay, I can now go like 10.2 millimoles per liter of lactate within my blood. And the reason for that is with regular training, we see that athletes become tougher, right? Our pain tolerance does go up. And that's essentially what this is measuring here, because this freaking hurts, right? So how much are you willing to hurt becomes more comfortable the more you do it. I know that sounds super weird, but you know, I always tell my athletes, like, get comfortable being uncomfortable, right? Enjoy this pain, right? Because that is what makes you better. That is what makes you faster, right? So again, more highly trained individuals are able to kind of top out those metabolic waste products because they have a higher pain tolerance. Their body is used to feeling that particular way. Okay, so again, that kind of gives us some of the details associated with the anaerobic glycolytic system, or that lactic acid system. And now we're on to the most complicated of the three systems, the oxidative system. Okay, and so now we are going to discuss really 3 different processes that are going to occur. And again, oxidative metabolism will now occur inside the mitochondria of the cell. Some of the pros and cons associated with using this system. It's slow to be activated, so that's certainly a con, but we have kind of an unlimited amount of ATP that we can get out of this particular pathway. So it's very fatigue resistant. Okay, so it's slow to be activated, not super powerful, but again, we have a unlimited supply essentially of ATP. Okay, so again, we said the first process is aerobic glycolysis. And I want to kind of review the difference between aerobic glycolysis and anaerobic glycolysis. So again, with anaerobic glycolysis, I produced pyruvic acid or pyruvate, and that resulted in lactic acid, and we just talked about that. Sorry. As it's associated with the lactate threshold, okay? Now, if I do have enough oxygen available, I'm going to choose the aerobic pathway. And again, my body would prefer to choose that aerobic pathway if at all possible. Okay, so with aerobic glycolysis, I am going to take that glucose molecule, I'm going to convert it into pyruvic acid or pyruvate, and then I'm ready to convert it into acetyl-CoA, which we'll look at next. Okay, so again, if I want to be aerobic in nature, I'm going to convert that pyruvate into acetyl-CoA, and then that acetyl-CoA will enter into the mitochondria, which will lead into the Krebs cycle next. Okay, if I don't have enough oxygen available, and that's because my energy demand is so high, I will take some of that pyruvate and convert it into lactate, and again, you know that as the anaerobic glycolytic pathway. Okay. Again, I have this in here several times, so it must be really important when we think about the difference between anaerobic and aerobic glycolysis. So again, glycolysis is a term that just allows us to break down glucose molecules into ATP. So if those glucose molecules are converted into acetyl-CoA, then it's known as aerobic. If that pyruvate is converted into lactate, then it's known as anaerobic in nature. Okay, so again, just want you to appreciate the complexity of this particular pathway. I'm certainly not going to test you on all of these things that happen within glycolysis, but again, remember that there are 10 to 12 different enzymatic reactions occurring in order for us to build this teddy bear, if you remember our example from the previous slides. So again, glucose is converted into pyruvate, and then we decide what to do next, whether we want to go lactate or do we want to go acetyl-CoA. So again, if I want to complete this aerobic pathway, in order for this to be aerobic glycolysis, I need to take that pyruvate. Again, glycolysis occurred inside the cell cytosol, and now I'm going to take this pyruvate and move it inside the mitochondria as I convert it into acetyl-CoA. Okay, so the key linkage between glycolysis and the Krebs cycle is the enzyme pyruvate dehydrogenase, and that is the enzyme also known as PDH. Okay, that is the enzyme associated with allowing this process to occur. So the conversion of pyruvate into acetyl-CoA involves the enzyme of PDH. Okay, so now let's take a look at what this whole Krebs cycle is. Okay, Krebs cycle, also known as the citric acid cycle. If that's confusing for you, again, I spent like a few years of my college days like trying to figure out what the difference was between the citric acid cycle and the Krebs cycle. They're the same thing, okay? So don't be confused, right? They're the same exact thing. We just have different terms for them, right? So the Krebs cycle, again, is going to occur inside of the mitochondria, and we need that acetyl-CoA in order for this process to go, Okay. What do we get out of this process? We get 1 ATP, we get 3 NADH, and 1 FADH. Again, these will come back and we'll be able to cash these in the next step, right? So these are like vouchers for energy that we can cash in a little bit later on. Okay. Other things to note about the Krebs cycle. This is the first time where we're going to talk about something that's not a carb, okay? So in the ATP phosphocreatine system and in anaerobic glycolysis, we could only use carbs, okay? We could only exclusively use carbohydrates as our primary like starting point, okay? So now that we're in the Krebs cycle or the citric acid cycle, this is the first time that we're able to incorporate some other types of fuels if we need to. So we can incorporate fats or proteins into this pathway if we need to, right? So this is the first time that that's happened. So again, let me repeat that. I have to use carbohydrates if I am going to use the ATP phosphocreatine system. I have to use carbohydrates if I'm going to use the lactic acid system, okay? So again, I want you to imagine this Krebs cycle as like a recipe. And imagine that this recipe was going to allow us to produce chocolate chip cookies, okay? So again, some of you will be surprised by these facts, but if I'm going to make chocolate chip cookies and I'm very creative and I don't always have all the ingredients that I need, right? So I need like chocolate chips, I need eggs, I need flour, I need butter, I need vanilla, etc. in order to make chocolate chip cookies. Yes? Okay. However, let's imagine that I ran out of eggs. I didn't have enough eggs. Okay. So one thing that I could do, again, imagine that this was the eggs in the recipe. So if I don't have eggs, instead of using eggs or just being like, well, shit, I can't make the cookies, I can put applesauce in place of the eggs, okay? Imagine that I didn't have the sticks of butter that I needed to make the chocolate chip cookies, okay? So instead, I could substitute in something like oil, okay? And so I can use oil instead of butter in order to kind of substitute that in, right? Again, lots of different options here in terms of substitutions if I don't have some of those ingredients, and that's great, okay? But what's the one thing I need, I absolutely have to have in order to make chocolate chip cookies, right? I absolutely have to have chocolate chips or it's just not going to work, right? So imagine that carbohydrates in this recipe are the chocolate chips. I absolutely have to have those chocolate chips in order for this process to work. However, I can substitute in the applesauce, which maybe is a fat molecule, and I can substitute in the oils, which maybe is an amino acid or something along those lines, okay? So fats burn in a carbohydrate flame. And what I mean by that is I have to have the chocolate chips, which are the carbohydrates in this particular scenario, in order for this process to work. Okay, so I have to have chocolate chips in order for the process to work. So I have to have carbs as kind of the backbone of the system in order for the system to be a go. However, I can substitute in fats. I could also substitute in some amino acids if I need to. Okay. So that's cool. I think the electron transport chain is pretty cool as well. So we talked about the Krebs cycle and what we produced out of that kind of recipe. So now we're ready to take a look at the final process associated with aerobic metabolism, and that is known as the electron transport chain. Okay, so this is going to occur on the inner mitochondrial membrane. Let's see if I can draw what this kind of looks like. Okay. Again, imagine my mitochondria kind of looks like a mandarin orange. I know I should stick to science and not art. Okay, so imagine that that's my mitochondria. Okay, it's double lined. Okay, so there's two different linings. There's an inner mitochondrial membrane, which you can see here, and then there's the outer mitochondrial membrane. Okay, the Krebs cycle, or that citric acid cycle, occurs like inside, like in the middle here. Okay, the electron transport chain is going to occur on the inner mitochondrial membrane. So, like here. Okay, all around the inside of the cell, or I'm sorry, all around the inside of the mitochondria, if that makes sense. And basically, this involves the transfer of electrons down an assembly line from an area of electronegativity to an area of electropositivity. Oxygen serves as the final electron acceptor. So this is actually the first time we've talked about oxygen. This is the first time we're actually using oxygen, and the only location where we're using oxygen. However, the electron transport chain is super important in the process of metabolism. And this particular little ditty that we're going to talk about accounts for about 90% of energy production. So super, super important. Okay, so here you can see what I'm talking about with this electro negativity and electropositivity. Okay, so again, I have these different electron carriers. I'm going to take either NADH or FADH. Again, we said that those were tokens that we could cache in later. So I'm going to take those and I'm going to shuttle an electron into this area. So this is the space between the inner mitochondrial membrane and the outer mitochondrial membrane. Okay. So I'm going to shuttle all these electrons into this area. So notice that they're highly concentrated in this area. So let me scroll back here. So again, that's this area between those linings. And it's very positive in nature because I'm shuttling those molecules to this area. So very positive in this little section in comparison to inside. It's a little more negative. Okay. So again, I want you to imagine that you're one of these H plus molecules. It's very positive out here and it's pretty crowded. Okay, so what I want to do is I want to flow down my concentration gradient and my electrical gradient. Okay, so I'm going to flow down my electrochemical gradient in order for me to get back inside here. Okay, and through doing that, I'm going to move through this ATPase pump, and that's what produces ATP. Okay. So it's simply the movement of these molecules through a simple diffusion through this ATP synthase pump that's going to produce 90% of the energy that we have. Okay. So again, this electrochemical gradient is generated via the flow of protons that represents stored potential energy. So again, concentration is high out here, or the chemical gradient is good. There's a lot of H on the out here and less H inside. So I want to move from outside to inside. Okay. And again, there's also an electrical gradient as well. It's more positive out here and less positive in here. Okay. So again, that's important for us. We want to move through this electrochemical gradient through this ATP synthase pump, which is shown here. And basically what happens is those H molecules are going to flow through this. Imagine it's like a merry-go-round, okay? As the merry-go-round is activated and starts spinning, that allows us to take ADP and convert it into ATP. And that's all good and great because that's what gives us energy. Okay. Well, how much energy, you might be wondering. Okay. So the electron transport chain, again, essentially all we do is we move those protons down the electrochemical gradient through that ATPase pump. So we get 3 ATPs per NADH and 2 ATPs per FADH. After the ATP is produced, we're going to use a translocase pump to move the ATP from inside the mitochondria to out into the cell. Okay, so again, imagine that I'm a good artist, I know. Okay, so imagine that I'm producing all these ATP inside the mitochondria, but like I'm using them outside here because this is where muscle contraction occurs, is in the cell cytosol. So basically with a translocase pump, I'm just going to swap them, okay? So I'm going to take the ADP, I'm going to shuttle them into the mitochondria, and I'm going to swap it out for the ATP. And that's what this translocase pump is. It's known as an antiporter. So basically, one item is moving in one direction, the other is moving in the other direction. Okay. Chemoosmotic coupling. So the coupling of electron transfer to ATP synthesis is indirect, but it involves two components. We have to move those electrons down their electrochemical gradient. And then secondly, we have to use that ATP synthase pump to allow them to flow down down that gradient in order for us to synthesize new ATP. Again, as I already mentioned, 90% of our ATP is going to be produced through the electron transport chain. Again, what sports or what activities would this system be important for? Really anything that's greater than 2 minutes in duration. And again, we're looking at moderate to low intensity. So any type of aerobic activity, sport, again, this is kind of your standard for everyday living as well. We're using aerobic metabolism to get most of our energy when we're at rest and just kind of hanging out. Okay. Again, I'm probably not going to ask you in specific detail about the number of ATP molecules produced. However, I do want you to appreciate the difference when we look at carbohydrates versus fats. Okay, so within glycolysis, we're going to produce 2 to 3 ATP molecules. Within the Krebs cycle, we're going to produce 2 ATP molecules. However, we got a fair amount of FADH and NADH that we could cache in a little bit later. So then in the electron transport chain, we have 34 ATP molecules for a total of around 39 ATP molecules per glucose molecule. Okay. Again, a nice summary for you as it relates to what happens with carbohydrate metabolism. So again, I can start as glucose and I'm broken down into pyruvate, and we know that process to be called glycolysis. Then I'm going to move that pyruvate into the mitochondria as it's converted into acetyl-CoA. That will enter into the Krebs cycle or that citric acid cycle. I get some ATP, but not a whole lot. I mostly get these vouchers for NADH, FADH. Then I'm going to go to electron transport chain. That's my money maker for energy, and I'm going to produce a shit ton of ATP in that particular pathway. Okay, so again, that gives us a good summary of what's happening with carbohydrate breakdown. Again, probably, yeah, the most complicated of the metabolic processes. Okay, so lipolysis is the breakdown of fat molecules so that we can use those for energy. So again, imagine that we are having a fat molecule in the form of a triglyceride, and that's going to be stored inside of a fat cell. Okay, so first thing I need to do is have this thing called hormone-sensitive lipase. And hormone-sensitive lipase is going to take a triglyceride molecule and break it into free fatty acids. So again, if you remember back to the digestive unit, a triglyceride is made of like a glycerol backbone, which is here. Okay, glycerol backbone and 3 fatty acid tails. Okay, so hormone sensitive lipase is going to go to this triglyceride, which is how it was stored, and release free fatty acids. So it's going to like nip these off. Okay, it's going to nip off each of those tails. Free fatty acids are carried into the blood, and then they're going to move to active tissue, so like the muscles. so that they can eventually be used as a fuel. Okay, so next the free fatty acids will enter into the skeletal muscle. They become activated, which requires us to invest a little bit of ATP. So we're going to invest 2 ATPs. Um, Fatty acids are then carried into the mitochondria for a process known as beta oxidation. And beta oxidation is basically taking those fatty acids and converting them into acetyl-CoA molecules. So again, you've heard of acetyl-CoA before because again, that was the gateway for sugars to get into the Krebs cycle. It's also the gateway for fats to get into the Krebs cycle. So beta oxidation involves fatty acids becoming acetyl-CoA molecules. Okay. So again, this just shows you what beta oxidation looks like. Acetyl-CoA molecules are cleaved off of the fatty acid chain. So again, each acetyl-CoA molecule, without getting too chemical with you, is a 2-carbon molecule. So again, I'm going to nip off that one. Here's 2 acetyl-CoAs. Here's 3 acetyl-CoAs. Here's 4, etc. Right? So again, this is just one fatty acid tail, and look, I'm able to get like 6 acetyl-CoAs out of it. Okay, with a glucose molecule or a sugar molecule, we only got like 2 acetyl-CoAs out of the deal, right? So again, once I have them in the form of acetyl-CoA, they're going to be fed into the Krebs cycle, which we know takes place inside the mitochondria. Okay. So how much energy do we get out of this deal? Again, we said that there was a little bit of a initiation fee of about 2. So we invest 2 molecules in order for us to get the fat activated. Then if I had 8 acetyl-CoAs, that will give us 16 ATPs in the Krebs cycle and about 80 ATPs in the electron transport chain for a grand total of 129 ATPs per triglyceride molecule. All right. So again, my point is that there's a lot of energy stored in one fat molecule, which is why our body likes to store things in the form of fats. Okay. So significantly more energy out of fats in comparison to what we got out of one carb. Okay. One thing that we haven't talked about is proteins and how proteins like play into this. Some amino acids are known as glucogenic, which means that they can be converted into glucose, so that they can follow kind of those same steps as what we saw with sugar. However, the problem associated with using protein as an energy source, it produces a waste product known as urea, which can be problematic because it impacts our pH levels. And also protein has many other unique functions separate from simply providing us with energy. So it's best to try and leave our energy production to carbs and fats because that's what they're there for, and save those proteins for building and repair within the cells when possible. Okay. Again, we can think about these systems separately, most certainly, but in reality, all 3 systems are working all the time. So again, when we say like, oh, at high intensity, we're using that ATP phosphocreatine system, yes, that's true. But what we really mean is that system is dominating. We're still getting a little bit of contribution from the other 2 systems. Again, so we're trying to differentiate which system is like dominating, which system is providing the most energy for us. However, they're all working together at the same time. Take-home message, again, phosphocreatine system is quick to be activated but can only go for a short period of time, whereas fat oxidation, again, we talked about lipolysis and beta oxidation and those issues, slow to be activated, but energy production is unlimited. Again, we've got like, I'm not trying to call you fat, but we have like 70,000 calories of fat stored within the body. So a significant amount of energy stored. And again, that's just your average person. So a lot of energy available in the storage of fat molecules. So energy production is essentially unlimited if we could just use, exclusively fats as a fuel. Okay. Again, kind of another little summary here so you can see the phosphagen system, that ATP phosphocreatine system. Again, I set up to 12 seconds, but you could say 10 seconds in duration. Again, high intensity here. Like the lactic acid system or anaerobic glycolytic system, 1.3 to 1.6 minutes. Again, I said 90 seconds to 2 minutes in duration is kind of our topping out. And then those aerobic pathways, which again, we said were the most complicated of the three systems, can be essentially unlimited. Oops. Okay. That is it for energy metabolism. Again, I would say this is probably one of the most challenging of the units that we will cover. So if you do have questions, please, please, please feel free to reach out and we can discuss those. All right, have a great day.